Good afternoon, everyone. We will wait for another 2 minutes for new participants. Okay, we start here. Good afternoon, everyone. And here I am welcoming all for this knowledge sharing webinar session. Hope everyone is doing well. Surely this webinar will be very helpful and useful to everyone. So let us start. Just one thing, during the presentation, if you are having any doubts or queries, any questions, then put the questions into the chat session. After the completion of presentation, we will have a separate question answering session, and all the questions I will try to cover after the presentation. So let us start. So today's topic is transformer testing, and basically we will concentrating on transformer turns ratio measurement and our instrument, that is TTRM, transformer turns ratio meter. So overview of the today's webinar. In this webinar, we will see the basics and types of the transformers, what test we need to conduct, applicable IEC or Indian standards, testing classifications. Then we will see need and working principle of transformer turns ratio measurement. After that, the acceptance criteria given by IEC or IEEE or IS, that is tolerance limit that will be accepted for the turns ratio measurement. Then after we will see the relationship between turns ratio, voltage ratio. Then after we will see need of the excitation current and phase angle deviation test. After that, importance and what is the vector group detection test, what is vector group. Then after we will see our instrument details, that is TTRM, and after that we will see the basics of the TTRM, general arrangement and test lead sets. Then connections to the device under test, how to connect our instrument to the transformers, power transformers or distribution transformers, then current transformers, voltage transformers, like that. Then turns ratio, our TTRM specifications and advanced feature that we have implemented in our instrument. Then user manual, how to operate the instrument, indications, which what indications we have provided in the TTRM. Then some part about the software, that we are having a software that is C-Trans, and after that we will have a separate question answering session. So as everyone aware about the types of the transformers, basically transformers is divided into power and instrument type transformers. In the power transformers, power type transformers, we can say generator transformers that are using at the generating side or stepping up the voltage. Then after auto transformers to interconnecting two systems. So these auto transformers that will require. Then reactors basically used for the reactive power compensation purposes. and distribution transformers. The distribution type transformers, that is, we can say it is at the distribution side for stepping down the voltage, that is 33 kV, 11 kV to 440 volt, like that. And after that, instrument transformers. Basically, the instrument transformers like current transformers, voltage transformers, and capacity voltage transformers. The importance of the instrument transformers for the metering, that is measurement purpose and protection purpose, and somewhere it is a special type protection purpose. The current transformers having two types, that is metering and protection, also some special protection type transformers. Similarly, voltage transformers having two types, metering and protection type voltage transformers. Capacitive type transformers, we can say it is used for the voltage metering and protection, as well as for the PLCC, that is power line carrier communication purposes. So these are the basic types of the transformers. And types based on the different criteria, that is based on the voltage level, as everyone aware about step up and step down, based on the core medium, that is air core and iron core transformers. Almost 100% of power transformers and current transformers, that is iron core transformers. Based on the winding arrangement, we are having auto transformers, that is single winding transformer, two winding transformer, and three winding transformers. Or we can say it is a tertiary, primary, secondary, and tertiary winding. Okay. So based on the construction, there are two types, that is core type, shell type. Based on the type of supply, that is single phase transformers and three phase transformers, and based on the connections, that is star delta, delta star, star delta, delta star, and star zigzag. So that is star, delta, and zigzag. Three types of connections available. So we will just brief about the parts of the transformers. So basically, the main parts that we can say: core, winding, then OLTC, motor drive, tank, conservator, radiators, bushings, clamping frames, then tap leads. So these are the all types of the parts, and everyone aware about the importance of each and every part. So we will just focusing on main parts of the power transformer, that is core. Basically core, that is the material used for designing the core, silicon steel. Then winding, the winding is of copper material. Bushing, there are two types of the bushings, that is OIP and RIP, that we can say oil impregnated paper. Then OLTC, OLTC is one of the important component of the transformer, that is to use regulating voltage without interrupting the load current. This is the main importance of the OLTC. So various OLTCs are types of the OLTCs. The most common used OLTCs, that is inductive and resistive. So that is, we can say 30% of failures of the transformers is due to OLTC issues. So that it is important that to monitor and healthiness of the OLTC. So this is the OLTC. Then tank, we can say tank is also important part. Then oil. Oil is also important part, that is the mineral oil normally we are using in the transformer for the cooling purpose. Then IEEE, I have taken some data from IEEE paper, and here you can see the major reasons for the transformers failure or transformer faults. So here you can see about 29% of transformer faults due to electrical disturbances, that will be internal or external, insulation deterioration, the failure of the transformers or creation of fault, that is 18%. Then lightning, lightning, due to lightning, the failure of insulation, failure of winding, that is up to 16%. Moisture content in oil, the failure of the transformer, this is 7%. Loose connection, the failure of it is 13%. And inadequate maintenance, that is irregular of maintenance, the failure of the transformer percentage, it is a 13%. So if you concentrating on related parts failure of the transformer, we can say this also data I have taken from IEEE paper. The OLTC, the failure rate, it is around 26%. some paper like IEC, it is given that the failure of the OLTC is 30% or 35%. Then winding failure, it is 34%. The failure of the tank due to some external damages or internal damages, we can say, it is 21%. The failure of bushing, failure of insulation, 20%. Failure of core due to overheating or due to short circuit, like that, the failure of core, it is 5%. And other, that is cooling and secondary part, the failure of the transformer, it is 20%. So here we can conclude, or we can say, the failure of the transformer due to failure of winding and failure of OLTC, that is on-load tap changer, it is total around 60%. So important part is that we need to take care the transformer winding and to check the healthiness of OLTC. So now we will go ahead for the transformer testing. So here you can say, here I have taken all the parts and what are the reasons of the failure behind that, and after that which preventive and diagnostic tests we need to conduct on that. So here you can see the part that I have. The first part is the winding. The reasons of the failure of the winding, that is interturn short, due to interturn short, then due to open winding, or we can say poor connection, due to magnetic imbalance, due to increasing copper loss, due to, that is the heating of the winding, then mechanical damages due to winding during the transportation, during the shipment, we can say, then insulation degradation, the moisture content introduced in the insulation, then rise in a winding temperature, partial discharge or hotspot. So these are the main reasons behind the failure of the winding. So for that, we are having a different tests that we need to carry out to find out what is the exact reason of failure of the winding. So if we need to find out interturn short failure is there, so with the help of turns ratio test, winding resistance test, excitation current test, short circuit test, and SFRA test. So these are the tests. After that, by taking the results from this test, we can compare the results, that is base results, and we can find out is there any interturn short or not. So these are all the tests that we need to carry out. So similarly, to find out the open winding is there or not, so with the help of turns ratio test, winding resistance test, with their results we can easily find out. Similarly, magnetic imbalance test, so separate magnetic balance test is also available. Then load loss short circuit test is there. Then mechanical damages SFRA test is there. Then insulation degradation, so capacitance and tan delta partial discharge, DJ of oil. So these are the main tests that we need to carry out. Then rise in winding temperature. To check the rise in winding temperature, we are having a heat run test and a winding temperature indicator facility. Then for partial discharge, so partial discharge test and DJ of oil test. Similarly, if we see for the core failure, the reasons behind the core failure, core overheating, then no load or core, we can say no load or open circuit test is there. Mechanical damages of the core, harmonics on the load current. So with the help of excitation current test, we can find out is there any overheating or not. Then similarly, no load test is carried out. No load loss we can find out with the help of open circuit test, SFRA, and harmonic analysis on load. So these are the tests that we need to carry out to check the reasons behind the failure of the core. Similarly, bushing, or we can say insulation, the insulation degradation we can find out with the help of capacitance tan delta and DC insulation resistance test. Similarly, second one, that is dielectric or high voltage test. So these three tests, that is lightning impulse voltage withstand, switching impulse voltage withstand, and power frequency voltage withstand. These are the type tests that we need to carry out at the type of type testing. So this test only carried all the three tests, that is lightning impulse, switching impulse, power frequency, that only carried out during the type testing product. These are the tests Then oil leakage test, that is visual check and oil level indicator is there to check the oil leakage. For insulating oil purpose, to check the insulation oil, the reasons behind the failure: rise in oil temperature, dielectric strength, moisture in oil, oil quality. So with the help of test, that is oil temperature indicator, we can find out the rise in oil temperature or not. So with the help of oil breakdown voltage test, we can find out. We can test with the help of dielectric strength. We can check with the help of oil BDV. And similarly, other tests, that is capacitance and tan delta, 4-point, and all the tests that we can do with the help of other tests. Similarly, tank, visual inspection and earthing. So all the that is the drain hole, oil level indicator, oil leakage, rusting and painting, we can check to check the healthiness of the tank. Similarly, OLTC. So there are different tests, that is winding resistance, continuity test, operation test, like that. To check the breather, that is silica gel, that is used for the check the healthiness of the breather. If there is any problem, then blue silica gel, that will be color will be changed to pink. Okay, so these are the applicable standards that have given by IEC, IEEE and IS that we need to follow during the testing. For the power transformer, the IEC, applicable IEC 60076, similarly applicable IS standard, that is 2026, and IEEE C57. Similarly, for distribution transformer, the IEC 600, same IEC that is applicable for power and distribution transformer, but IS it is 1180. Similarly, all the that is GIS circuit breaker I have given here for your information purpose only. For the current transformer, that is IEC 61869-1 and 2. For the reactors, IEC is same, that is 60076. IS it is 5553 and IEEE C57. So these are the applicable IEC, IS and IEEE standards that we need to follow during the testing, during the design, and during the quality check purpose. So here I have given some summary about the major tests that we need to carry out on a power transformer. So here you can see the name of the test I have given. After that, I have given a reference IEC standard with their clause and reference IS standard with their clause. So these are the basic tests or major and important tests that we need to carry out on a transformers, that is power transformers and distribution transformers. So you can see winding resistance, turns ratio, vector group or polarity, short circuit, open circuit, magnetizing current, dielectric tests, or OLTC healthiness, then BDV, heat run, tan delta, SFRA, magnetic balance. Out of that, turns ratio test, vector group, polarity, magnetizing current, and magnetic balance. So out of all the tests, that is around 4 to 5 tests that we can do with the help of our single instrument, the named as TTRM. So with the help of TTRM, we can find out transformer turns ratio, transformer voltage ratio, vector group detection, polarity of single phase, then magnetizing current of single phase as well as 3-phase transformer, and magnetic balance. Basically, magnetic balance test is not recommended by IEC or IEEE, but in India it is basically all the customers are doing the test. It is recommended and given the information in CBIP standard. So with the help of TTRM, we can do all the tests. That is the 5 tests we can do with our single instrument named as TTRM, transformer turns ratio measurement. Okay, so testing classification, as everyone are aware about the testing classification, the testing, it is divided into type test, factory test, commissioning test, routine test, special test. That is type test, it is carried out to verify on a first prototype, that is first product, to prove the ratings and characteristics, and this test is valid. Is there any no change, no design change? Factory test to check the designed product is as per the specification, as per the rating. Commissioning test, that is need to do at the time of commissioning or after the commissioning. Routine test that we need to carry out once in a year or twice in a year as per recommended by different standards to check the equipment condition, and special test as per the special requirement of the customer. So these are the testing classifications. Here you can see this is our TTRM instrument. So with that we can do the 5 tests that we will see in the next slide. So basically, as we have seen, transformer turns ratio measurement, it is a common test that is covered in a different international standards. That is, I said earlier, that is IEC 60076-1 clause 10.3. Similarly, IEEE C57, ANSI standard, that is C57, and IS 2026-1 clause 10.3. Okay, so this test is recommended in all the standards. So next part is the main reasons of the transformer winding failure. So basically, main reasons of the transformer winding failure is due to the dielectric problem or insulation failure. Also, we can say due to the heating effect, due to the copper line resistance thermal losses occurs. Due to that, winding failure occurs, or due to the mechanical faults, due to the or we can say due to the improper repair, bad maintenance, corrosion, manufacturing deficiencies, vibration, and mechanical movements within the transformer. So these are the main reasons of the winding failure. To evaluate the possible winding damages due to above mentioned problems, we are having a different test that we need to carry out to find out the exact reason behind the winding failure. Okay, so these are the tests. Here you can see turns ratio, percentage ratio error, phase angle deviation, excitation current, vector group, and magnetic balances. So with this test, we can easily analyze the winding healthiness or winding reason behind the winding failure. So we are having a different models of the TTRM. That is TTRM 302, TTRM 301, TTRM 102, TTRM 101. So here you can see TTRM 301 and 30 is for the 3-phase transformer testing, and TTRM 101 and 102 is for the single-phase transformer testing. So 302 and 102, it is an advanced model. So with that models we can find out maximum test, and TTRM 301 and 101, it is a basic model. So with that we can only test transformer turns ratio and transformer ratio error. And with the help of TTRM 302, here you can see, so these parameters we can find out, and this is for the 3-phase as well as single phase as well as 3-phase transformer. And TTRM 101 and 102, it is only for the single phase transformer. So with the help of TTRM 302, we can easily find out transformer turns ratio, voltage ratio, transformer ratio error, excitation current, phase angle deviation, vector group detection, automatic vector group detection facility is there, then magnetic balance test. Similarly, TTRM 101 and 301 and 101 is for the ratio and ratio error detection, and 102 is for the ratio error, excitation current, and phase angle of a single phase transformer. So these are the test parameters that we can find out with our various models. Now we will see importance, need of the different tests, and how we will carry it out with our instrument. So as everyone knows, the need of the transformer turns ratio measurement. So basically, transformer test we need to carry out to find out the transformer has the right ratio corresponding on its rated voltage in a primary and secondary. Also to verify the design specifications, to verify the quality of the manufacturing process, ensure the inductance property of the transformer. The transformer should have transformer winding should have the high inductance and should have the low resistance. So with the help of that test, we can find out the formation of flux due to the winding inductance. Okay, so to find out that the transformer is balanced or not, so it is recommended that all 3 phases should have the same turns ratio. After that, to find out whether the overheating or overcurrent condition shorted the turns, to find out that. Then this test is also applicable for applicable for current transformer and voltage transformers. As everyone knows that our protection system that relay current and voltage transformer takes the current, secondary current and secondary voltage, and that is connected to protective relays. If there is any interturn short, then CTs and VTs, the secondary voltage and current might change, and that will abnormally relay will work. So this problem will occur. So to test the turns ratio or ratio of the current transformer and voltage transformer, this is also very important. So here you can see some peaks of the damaged winding due to the interturn short. You can see due to the interturn short or hotspot, the short circuit happened. The working principle of transformer ratio measurement, turns ratio measurement, it is very simple. That here you can see the HV winding and LV winding. Some voltage we need to inject from the HV winding, and after that we need to measure LV voltage, and after that with the help of V1 by V2, that is HV voltage divided by LV voltage, we can find out the voltage ratio, and which is equal to turns ratio, that is HV turns divided by LV turns. Here you can see. So formula is simple, that is HV voltage divided by LV voltage and HV turns divided by LV turns. This is the basic formula that basic principle and basic formula that we have to use. Then tolerance limit and acceptance criteria. As I said earlier, so in different standards, IEC and IEEE have given some tolerance limits that that is the voltage ratio obtained is compared with the voltage ratio mentioned on the nameplate of the transformer or in a factory test report. That is, we need to take some base results, that is from nameplate of the transformer, or during the routine test or during the factory test, we have some test report that we can take as a base reports. Then after, we can say the ratio obtained by field test should be in a limit that is recommended by, it should be 0.5% of the base results, or we can say it is a factory result. So it should be in a limit, that is up to 5% tolerance will be acceptable. Above 0.5% will not be acceptable. Okay. Also some in some basic it is criteria applicable in some manufacturing, that for the new transformers, to check the good quality, the tolerance limit for the new transformer, it is 0.1%. Also, from time to time, it may be observed that the measured ratios of the outer phases of the three-phase transformers will be slightly different. That is, if you see RYB 3 phases are there, then R and B there should be same results, or but in somewhere it is observed that R and B results will not be same. That will happen, but unless the difference of both the phases are above 0.5%, then only we can say the transformer having some issue, and we will go for the rejection purposes. So this thing we need to consider. So so now we will see what is the relation and what is the formula to convert the voltage ratio into turns ratio. So for that single phase, turns ratio is always equal to voltage ratio. Also for three-phase transformers, if connection is star-star, then voltage ratio is equal to turns ratio. If it is a star-delta transformer, then turns ratio is always equal to voltage ratio divided by √3. For delta star transformer, turns ratio is equal to voltage ratio into √3, and for delta turns ratio is equal to voltage ratio. So these are the this is the relationship of turns ratio and voltage ratio for single phase and three-phase transformers with various connections, that is star-star, star-delta, delta star, and delta-delta. So next one is the how to calculate the percentage error of the turns ratio. The formula is simple, that is percentage error is equal to measured ratio minus calculated ratio. Measured ratio is from our instrument, and calculated means this is from the nameplate readings, divided by calculated ratio into 100. That is directly we will get a percentage error. Now the deviation of the ratio, that is turns ratio or voltage ratio, from the expected values may indicate the followings. That is during the manufacturing, we can say during the manufacturing process, the manufacturing defects in a winding may occur due to improper turns. If there is an improper turn, incorrect polarity, incorrect winding configuration, that will give a deviation of the turns ratio. If there is any insulation failure, that is damaged turns to turn insulation, resulting in shorted windings. Major insulation failure, that will give inter winding or ground to ground fault, that will directly gives the deviation in the turns ratio. If is there any defective tap changer, then we can say the incorrect assembly of the winding connection in the OLTC, high resistance connections, and incorrect tap changer setting. So these are the main problems that will occur in a tap changer that will give us a deviation in the ratio. So these are the main expected reasons for the deviation in the ratio during the manufacturing phase, during the insulation failure, or we can say at the time if there is any issue in the tap changer. So next part is the need of the excitation current test. Then next question arises in our point after turns ratio, we are getting results, and we can compare with the base results, and we will get a reason, or we can check with healthiness of the winding. But what is the importance of the excitation current test? Excitation current test is also important to analyze the shorted turns, open turns in the winding. That will also we can find out with the help of turns ratio test. But with the help of excitation current, we can easily find out the condition change in the effective reluctance of the magnetic circuit. That is the affecting the current required to establish the flux in the core. Also to track the movement of the core, magnetic core structure, shifting or deshaping of the winding. So with the help of excitation current, we can easily find out. Now here you can see this is a circuit diagram of transformer. Here you can see whenever we are giving some voltage to the transformer primary, after that excitation current will flow, that will require to create a flux in the primary as well as secondary winding. Here you can see in the first circuit diagram, secondary is always secondary we have taken open, and we are giving some voltage. After that magnetizing current will flow from primary, and after that flux, that is flux will be flowing from primary to secondary, and EMF will be induced in the secondary winding easily. That time the magnetizing current which is required, I magnetizing. Let us consider this is the I magnetizing. If is there any interturn short occurs in the primary or secondary, that will act as a load, or we can say that will act as a fault. And after that, if there any short circuit, short interturn short happens, then some fault current will flow from the secondary winding in the opposite direction, and after that the flux, that is the created flux by interturn short I fault current, that will flow in the opposite direction of the I magnetization, that is a flux produced by I magnetization, and that will nullify and try to nullify the I magnetization. So to recover the I magnetization flux, to recover that flux, that will we will require an extra flux that we need to create. That is why we require additional excitation current that we need to flow from the primary side. That is to nullify the I fault or flux created by fault current. So with that we can say excitation current will increases. So if excitation current, we can if results of the excitation currents are different, that is increasing excitation current will directly we can say that if there is any interturn short happens in the primary or secondary winding. So this is the test that we also easily find out the interturn short or not. So for analysis of the excitation current test, given some recommendation to analyze the test results or the three-phase units. Normally it is given that readings, all the readings less than 50 milliampere, the difference should not exceed 10%. If the readings are greater than 50 milliamperes, then difference says should not exceed 5%. Normally there are two similar readings, higher readings on two outer limbs, and middle core or middle limb will have some amount of excitation current. That is, outer limbs should have this higher excitation current with comparison of the middle limb. Then after phase angle deviation, so phase angle deviation test, it is to find out the phase angle difference between HV winding voltage and LV winding voltage. Generally this difference is very small, but it can change drastically if there is any transformer core is damaged. After that we will get a wrong phase deviation. That is why the phase angle deviation test is important. Then need of the vector group test. As everyone aware about, vector group test is applicable for the single phase, for the three-phase transformers only, to find out the vector group, that is different types of connection, that is star, delta, and zigzag type of connections are there. Basically the vector group checking or detection is important before connecting two transformers in a parallel. If we connect two transformers having a different vector groups in a parallel, then chance of short circuit happens due to unnecessary flowing of circulating current from one bus to another bus. So this is the basic reason to test vector group before connecting two transformers in a parallel. Here you can see. So basically different types of the connections, that is star, 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 delta, star, zigzag, like that. Polarity, as I said, vector group test is applicable for three-phase transformer. Similarly, for the single-phase transformer, polarity test is important. In the polarity test, there are two types, that is additive polarity or subtractive polarity. In the polarity test, we just find out the formation of flux in the which direction. If additive polarity is there, then formation of current in the same direction. If subtractive polarity is there, the formation of flux with respect to primary, the formation of flux in the secondary with respect to primary, it is in opposite direction. So in our instrument TTRN 302, we have given a facility to detect about 76 to 80 vector groups we can easily find out. Vector group detection notification. If you see in the nameplate, you can get capital Y, capital N. It indicates that capital Y indicates that it is a HV winding, and N indicates it is a neutral. If small n and small neutral is there, we can say it is a star in a LV winding, and N, it is a neutral at the LV winding, and 0, this is the phase deviation, that is phase angle deviation, phase angle displacement between HV and LV. So overall you can say capital Y, capital N, small y, small n, 0. That is star with neutral in HV winding, star with neutral in the LV winding, with phase deviation, phase displacement 0. Here you can say, just I have added some examples for your information purpose. That is Y0, Y is capital Y, this is a for HV star, small y, this is LV star, and 0 is the 0 angle phase displacement. Similarly DD0, that is delta, phase angle deviation, it is a 0. If it is a Y by 6, that indicates that star is a HV, star is in a LV, and phase angle difference between HV to LV, it is a 6. 6 indicates this is 6 into 30 degree. 1 is for 30 degree, 6 into 30 is equal to 180 degree. That is phase angle difference between HV to LV voltages, that is 180 degree. Here you can see. Similarly, DD6 is there. If it is YD1, that is phase angle with respect to star to delta, it is 30 degree. And similarly for delta Y. So here you can see about 76 vector groups are there, and we have added in our instrument to find out the vector groups. That is, here you can see all the vector groups, that is with respect to star to neutral, with respect to star delta, then with respect to star zigzag, like that. So around 76 vector groups we have added. So as I said, parallel connection of the transformer. So this is transformer A, this is transformer B. These are two connected in a single supply bus 1 and bus 2. And if you connect two transformers having a different vector groups, that will happen. Unnecessary circulating current will flow from this bus, this transformer to this transformer, and unnecessary will happen. Circulating current will flow, and that will damage the system. So that is why before connecting two transformers, we should have to check the vector group. Magnetic balance test. So this test is, as I said, this test is not recommended by any IEC or IEEE standard, but this test is commonly doing by all the manufacturer to check check the magnetic imbalance or magnetic balance of the core. So basically here you can see this test is not applicable for the single phase transformer. This test is applicable for 3-phase transformers only. So to check or identify interturn faults or magnetic imbalance due to magnetic core structure shifting or de-shaping of the winding. So with the help of that, we can easily check. So this test is simple. We need to inject some voltage in a one phase, and after that we need to measure voltage induced in the another two phases. That is, if we inject some voltage in R phase, and after that we need to measure voltage induced in the produced in the Y and B phases. So having some criteria that the core or to check the magnetic balance or not. So if we see, if we inject a voltage on R phase, and now after that we can check voltages on Y and B phase. There will be a criteria, that is Y volt, the produced voltage. If you inject 100% voltages on 100% voltage on R phase, then the produced voltage on Y and B phase, that is up 60 to 90% voltage should be present in the Y, and by B phase it is 10 to 40%. So this criteria we need to follow. Similarly, if we inject some voltage on middle phase, then outer two phases should have produced voltage is 50%. And the identical results confirm no damage due to transportation. If zero voltages or any negligible voltages induced in other two windings, so we can say, we can investigate there should be a problem. So this is all about the magnetic balance test. So now we will go ahead with our instrument details. That is instrument TTRM, and this is our front panel of our TTRM. So here you can see, so we have given one indicates this is a mains inlet. Then we have given one on and off switch for starting and for on and off purpose. Then we have given inbuilt a 5.7 touchscreen display for human interfacing. We can easily operate the instrument with our hand, and then here you can see different connectors we have given. So HV connector, LV connector, and OLTC control. That is HV connector is to connect on HV side of the transformer. LV connector is need to connect on a LV side of the transformer. OLDC control cable we have given, that is automatic OLDC control facility we have provided in our instrument. That is to measure all the taps turns ratio, all taps turns ratio, excitation, current, phase angle deviation in a single click. That will reduce the time for the testing. Then master earthing cable we have provided, master earthing port. Then emergency stop. If you want to stop the test in emergency case, then we can easily stop the test. So that is why we have given emergency stop button. Then printer option we have provided to print out the results for the future use. Then Ethernet, that is to connect instrument to the PC for data downloading, uploading purposes. Then data report creation purposes. So with the help of software, we can easily take through Ethernet port. Then USB port for data storage purposes we have given. So USB and Ethernet facility is there. So these are the test lead set. Here you can see that is as per the requirement. Normally, as a standard scope of supply, we are providing 15 meter HV cable, 15 meter LV cable, OLTC control cable for OLTC operation, for rising and lowering the taps, then Ethernet cable, master earthing cable, and AC mains cable. So these are the major test lead sets that we are providing with our instrument TTRM. Now, how to connect instrument with transformer. So this is instrument, the point is HV and LV. From HV connector there are 4 points, that is 4 cables, R, Y, B and neutral. That if it is a star transformer, that is HV cable for all the 4 points, that is R, Y, B, neutral, we need to connect directly. Similarly LV 4 points, that is we need to connect directly, R, Y, B, neutral. If it is a star delta, then we need to connect HV points to RYB neutral, and LV RYB neutral we need to connect to the transformer RYB, and remaining point, that is N2 cable, that we need to not to connect. This is an open condition. Then star delta, similarly for delta star, HV cables, that RYB cables, that only we need to connect to the RYB of the transformer, and LV, that is 4 points, that is RYB neutral, that we need to connect to the transformer LV point. If it is delta, only RYB of primary or HV, and similarly RYB of LV, that we need to connect. If it is a single phase transformer, then only HV points, that is R and neutral, that we need to connect. Other remaining ports that not connected, that is B and Y and B. Similarly at LV side, only connect R and neutral, and other remaining cables, that is Y and B, that not connected. If it is auto transformer, in that case, that HV cable we need to connect to the HV point, that is from R2 neutral, here you can see U1 to neutral, and LV cable that we need to connect to U2 to neutral, that is U2 to neutral, that is U2 and N2, and other remaining cables that not connected. Also, as I said, this instrument is very useful for testing of ratio, turns ratio of the current transformer as well. Here you can see the transformer primary is here, and transformer secondary is here, that is U2 and N2, that is from LV port, that we need to connect on a transformer, current transformer's primary, and HV port, that is U1 and N1, that we need to connect on a secondary. Basically, if you see, HV point that we connect on a secondary side, and LV cables that we need to connect on a primary side. So these are the some major specifications of our different models, TTRM 302, 301, 102 and 101. So as I said, TTRM 302 and 301 is for 3-phase transformer testing. Then TTRM 101 and 102 is for single phase testing, and the ratio range is common for all the models, that is 0.8 to 20,000 tons, that is we can measure. And best accuracy that we are providing, that is 0.03% at 100 volt with resolution, 5-digit resolution is there. And different excitation voltage ranges we are having, that is 10 volt, 40 volt and 100 volt. So for doing power transformer, we can test up to 100 volt from 10 volt. If we are testing on current transformer, it is normally recommended to test on 10 volt only or 40 volt only. And for voltage transformer, we can do 10 volt, 40 volt and 100 volt. But for current transformers, we can only use 10 volt and 40 volt. And phase angle deviation range that we have provided in our advanced model, that is TTRM 302 and 101, and the range is plus minus 180 degree. Excitation current measuring facility we have provided, that is up to 2000 milliampere, that is 2 ampere. Then, as I said, raise and lower tap position automatic from the instrument facility we have provided. Communication interface, that is Ethernet and USB facility we have provided. Ethernet is for PC connection and USB is for the storage device interfacing purpose. Then printer facility we have provided. We are having an inbuilt printer in the instrument, display, touchscreen 5.7 inch display. Then test cables as per the requirement, we can provide. Then operating temperature is minus 20 to 55 degree and weight is approximately 10 kg. So here we can say the instrument is very simple, and for the operation purpose to measure different tests, this is very useful. Now we will see in short the instrument features. What are the main features we are having in our instrument? So basically the instrument is designed, that is advanced microprocessor based design is there. Measurement of ratio of all the phases in single test or single click with percentage error is possible. Automatic operation of OLTC and ratio calculation at all the taps and tabular results in a single click. This facility we have provided. Also phase angle deviation, magnetizing current and tap position detection facility we have provided. Then automatic factor group for 3-phase and polarity testing of single phase of a transformer is possible. Then inbuilt touchscreen display with simple menus to operate TTRM. Different voltage ranges we have provided to get highly accurate and repeatable readings. Facility to configure transformer IDs and details. Then date and time stamping to the results facility we have provided. Instrument is having inbuilt memory, that is up to 10,000 or 5,000 results we can save easily. Thermal printer facility we have provided to take the printouts. Ethernet and USB port facility we have provided, and instrument is very light and having and it is portable instrument that is housed in a
Hello, Kiran.
Yes, yes.
Yeah, you are
Yes,
back.
yes.
So you can start. Yeah.
Okay. Now about the instrument. So instrument has gone through all the type tests that is required as per recommended by IEC, IS, then some international standards to, that is from safety compliance point of view, ESP, EMI, EMC compliance, emission test, humidity test, environmental standards, storage test. That is some IEC standards. We can say IEC 60068, IEC 61000, ISC 161010, that is for safety. So instrument has gone all the tab test. Then after we will see the user interface for easy operation for the operator. So we have provided different options, that is testings, test, records, special functions, and help. Setting is for the creation of ID or edit of the ID purposes. And in the test we have given different types of the test, that is auto test, manual test, quick test. So these facilities we have provided. Records, in the records we can easily save the records or delete the records. In the special functions we have given facility for the time and date saving purpose. And in help we have given all the information about the instrument operation. So this is very simple instrument with the point of operation to that for doing a test. So different indications facility we have provided. If there any emergency stop we have pressed, then instrument will show that emergency stop is there, and release emergency stop to proceed. So this command indication will occur in a TTRM display. If overcurrent during the test, if excitation current is more than limit that we have set already, so that will give a command that is overcurrent. And also we have having the indications for the polarity. For the additive polarity, it will give a positive indication, positive sign, and for the negative or subtractive polarity, it will give a negative sign, plus and minus sign. Also, if you see about the PC software, so we are having a inbuilt, we can operate the, we can save and record, upload the results through PC for data downloading and report generation. So we can connect the instrument through Ethernet port directly to the laptop or PC. So here you can see in the front screen, we will get a TTRM model selection. So all the models that we will get, after that we need to select a model. And in menu bar, we have given options, that is to connect. Firstly, we need to connect, and in file, we can import and export the results. In setting, we can create ID, upload the ID in the instrument. In the tools, we can directly having a restore option is there. So here you can see the related about the PC software. Sample test report. Here you can see after the result, the instrument on the instrument display, we will get all the results, that is phases RYB, that is UVW, ratio we will get, then percentage error we will get, eye magnetization we will get, and phase angle deviation in a single click display. In a single view, we will get all the results. And if we take a printout, we are having option, that is to add location, then add ID, that is ICT or transformer details, serial number of transformer, make, then HV voltage, LV voltage, then number of phases, vector groups, then tappings, total number of taps, test voltage that's selected at the time of testing, that is 10 volt, 40 volt, or 100 volt. Then date addition, date, then date, test time, test date we will get, then tap position, and all the results of the tap position for all the phases, that is RYB, and for that we will get all the results, that is ratio, excitation current, percentage ratio error, and phase angle deviation in a single report. If we take a if we create a report through software, through PC, then we will get report like that. That is, we can add logo also. In the front, we will get TTRM 30 test report. After that, we will get a location of location, then transformer ID, vector groups, then serial number, all the details, that is LV voltage, HV voltage, number of phases, step voltage variation, then total number of taps, then tapping range, higher tapping range, then lower tapping range, then stop voltage variation. So these are all the details we will get at the header, and after that all the results of all the taps, that is if we consider taps are there 17, we will get all the results in all the 17 taps results in a single page and with date and time. Here you can see on tap number 1 date and time, then test voltage, this is 100 volt, ratio, percentage error, I magnetization current and phase angle deviation. Similarly for R phase, Y phase and B phase, we will get all the results of all the taps. So this is all about the transformer testing, transformer turns ratio measurement, and transformer turns ratio meter, that is our series TTRM. Now we will move ahead for the questioning and answering session. If you are having any queries, please put into the chat session. So one by one we will see.
Yeah, Kiran, there is one question by Mr. Manjunath Godar. So he is talking about what is the test period difference should be maintained. So you can elaborate that one, that no such thing. Actually, sir, it is something like as per every utility, they are having some specific schedules that every 3 months or every 6 months or yearly or yearly. Generally, as per the utility to utility, it varies. But if there any such standard or time difference is mentioned in IEC, Kiran?
In ISC, if you see,
Or trans ratio or vector group detection, is there any time period mentioned in IEC? You can highlight that one.
Only for turns ratio in IEC 60076, they have given for the routine test. They have mentioned that this test should be done once in a year. Okay, but other standards like IEEE and the Indian standard, they have not recommended anything about period of the testing. But IEC has recommended, so we need to do turns ratio test once in a year.
Yeah, but not for any other test.
Yes.
Yeah.
Other test has not given anything.
Whatever the other test we can do with the help of TTRM kit.
TTRM, yes.
Yeah. So, sir, this is the thing. So, generally, as I was telling, it is utility to utility. They are following their own standards. So, based on that one, whatever your you can decide for your organization or in that fashion. Mr. Kutub Sheikh has asked, can we do demagnetization through TTRM kit? Kiran, you can explain that why demagnetization is required and when demagnetization is required and how it is done. Because there is one more question that whether Scope is having any demagnetization kit or not. So you can explain first the why demagnetization is required, how demagnetization is done, and then what are the kits available like MACD and TRM. That thing you can, if you explain in detail.
Okay, so basically demagnetization test is important to nullify the residual flux that is created at the time of DC current, means that is resistance or transformer winding resistance test. That is to check the residual magnetism. Basically, residual magnetism leads to high current, high inrush current, which puts a great and unnecessary load on a transformer that could damage the transformer itself or other components like that. So for that, we need to do a demagnetization. If we see, if we take the results of transformer winding resistance, and after that we are immediately go for transformer turns ratio results, we will get a deviation on turns ratio results. Also, we will get a deviation on excitation current results. So it is recommended that after doing a DC current test, that is transformer winding resistance test, firstly we need to demagnetize the transformer, and after that we will go for we have to go for turns ratio and excitation current test. So this is basically test is added in a transformer winding resistance test. So after doing a winding resistance test, our responsibility to demagnetize the transformer. So that is why we have added the demagnetization feature in our transformer resistance measurement instrument. That is our instrument named TRM, and various models are there: TRM 25, TRM 25 plus, 50, TRM 50 and TRM 50 plus. The 50-25 indicates the maximum current that we can inject in the transformer, and there are various methods available to demagnetize the transformer. That is decreasing amplitude of alternating polarity DC current like that, constant voltage variable frequency source like that. So basically this test is important after doing a winding resistance test. That is why we have added in our winding resistance test kit. So this feature we have added in TRM 25, TRM 25 plus, 50 and 50 plus, and this is this feature we can use after the winding resistance test. So this is about the demagnetization.
Yeah. So Kiran and for Kutub sir, as Kiran has explained, this is majorly demagnetization is required only after the DC current injection test or DC resistance measurement test. Transformer turns ratio test being an AC test, generally after this test we do not require any demagnetization. So this is the demagnetization test. That's the reason specifically is not been included into the transformer turns ratio kit, as it is required after the winding resistance, DC winding resistance. So it has been added into our as a default feature into our winding resistance kits. However, if you want to use the standard demagnetization, means demagnetize the transformer as a standalone thing, you can do it with our TRM winding resistance meters, or you can do it, or else we are having one more kit with the high voltage. If you want to do it, we are having the MACD series of product, where you can use that one as a demagnetization. With that kit, you can also do the not only demagnetization but also the knee point voltage test also of the city. So MACD is that product that you can use, or you can use the TRM, or even for the standard demagnetization, even you can use the variac, a simple variac that can also be used. So this is in short how we can do the demagnetization, and why we have not given the demagnetization feature inside the TTRM kit. Surinder Singh sir, we can provide this winding resistance model, or for majority of our products can be supplied with 110 volt supply for 50 hertz or 60 hertz, as well as for 230 volt supplies also can be supplied. So as per at the time of ordering, if we know what are the country where you are going to use, or in some of our kits it is having the universal power supply, so we can supply both the options. Now for this transformer turns ratio, we are not having any battery inside the kit, because generally people are not using the battery inside transformer turns ratio. it is not at all recommended. Though some people used to ask, okay, for winding resistance, can I have the battery option? But for winding resistance, it is not recommended. And for transformer turns ratio, it is also not. People are generally not giving. So that's the reason it is being the AC. It is not provided the battery. It is a mains operated kit only. Kiran, any other question you want to take up?
One question asked by Santosh. For dry type transformer, what type of standards is applicable? So actually, for ISC 60076 is common for dry and oil type transformers. So no separate ISC standard is there. For IS also 2026 is applicable for both oil and dry. So no separate ISC standard is applicable for dry type. It is common for dry and oil type. So they have covered all the details regarding oil and regarding dry type transformers.
Yeah. Last question in the chat box is the Mr. Deepak says, can we measure the magnetic balance? Actually, sir, magnetic balance practically it is just checking sort of a thing. We are never measuring how much is the magnetic balance. Generally, for the magnetic balance test, we are giving the small voltage, maybe, and any voltage you can give into the middle limb. And you can, let's say, if you are giving it to the middle limb, you will be getting the generally half the voltage of that one into other two limbs. And if you are giving into the left side limb, then some reduced half the thing will be available in the central limb, and much lesser thing will be available into the extreme right hand side limb. So from that one only we are checking the magnetic balance with just a checking kind of a thing. We are not measuring the magnetic balance as such. So Kiran, am I right, or you want to add something on this magnetic balance test? Anything more?
No, sir. I have added one slide that in some standard recommended or given some recommendations that if we inject voltage on any phase, accordingly other two phases should have the limit. That is, if we inject 100 volt on R phase, then in Y phase there should be induced voltage should be from 50 to 70% of Y phase, and remaining voltage, that is 30% that will produce in other phase, that is Y phase. If we inject a voltage on middle phase, then around 40 to 50% on left side